All right, good morning, everybody. My name is Isaac Montoya, and I am the Director of Marketing here at Upsite Technologies. I would like to thank you all for joining us here today. We are here to talk about room-level airflow management and cooling optimization best practices. I will be joined here shortly by Rob Hudeman, Senior Vice President of Operations at Critical Environments Group, as well as Lars Strong, Senior Engineer and Company Science Officer with Upsite Technologies. Before I kick it off to Rob and Lars to jump into the presentation, I just want to quickly cover a couple of housekeeping items. Everybody will be muted on the call just to block out any background noises, but we do encourage you to ask questions. So if you'll notice in your Zoom dashboard, there's a Q&A module there that we would love for you to ask some questions and get some engagement going. We will answer as many questions as we can during the webinar, but we will have some time at the end of the presentation to address those questions out loud. In addition, if you have any technical difficulties, please feel free to shoot me a message through the chat option, and I will try my best to resolve that as quickly as possible. Lastly, I know we're still in the midst of this pandemic that is affecting everybody around the world. So I hope that everyone is staying safe and healthy. Obviously that is the highest priority right now. So I just hope that everyone and everyone's families, everyone's work colleagues, that everyone is staying healthy during this time. And hopefully we can do it as quickly as possible. All right, so let's tell you a little bit about Rob and Lars. So Rob Hudeman, as I mentioned, is the Senior Vice President of Operations at Critical Environments Group. Rob has over 30 years of industry experience in data centers and supporting infrastructure management in areas such as power, space, storage, cooling, and just overall operational best practices. Lars Strong, Senior Engineer and Company Science Officer, is a recognized thought leader in the industry. He has spoken at many industry events on topics regarding airflow management, best practices, and cooling optimization, and has many certifications to go along with that. So between Lars and Rob, there really is a wealth of knowledge and wealth of experience when it comes to optimizing the cooling infrastructure and in data centers and just really achieving operational efficiency. So they bring a lot to the table in this conversation, and we are glad to have them here. So without further ado, I'm going to pass this off to Lars Strong to get us started.
Thank you very much, Isaac. Well, I want to also say thank you very much for taking the time to join us. We're going to make this as valuable for you as possible. Rob and I have a lot of experience in the data center industry and around cooling optimization, and we hope to share that knowledge, that experience with you today, and as much of that as we can in this short hour that we have. So here's the agenda that we're going to go through today. We're going to just briefly talk about the 4 R's of airflow management, a concept Upsite developed, and then we're going to get into the concept of matching cooling capacity with the IT load and a few very important aspects of the science behind cooling optimization. We're going to discuss room airflow management best practices and then get into some of the solutions that are available to support the process. Rob's going to go a little deeper with that into artificial intelligence and machine learning solutions. And then, as Isaac mentioned, we're going to have some time at the end for questions. So please, along the way, type those questions in, and we'll get to as many of them as we possibly can at the end. All right, so the 4 R's is a concept that we developed to help focus efforts around both airflow management and cooling optimization. You see the 3 R's are in the outer circle, the rack, the row, and the raised floor. Each of those is an aspect of airflow management in the computer room that can be focused on. Projects can be initiated to really focus on rack airflow management or row or raised floor. And each of those 3 elements point to the room in the center, because the room is the location where adjustments need to be made to realize those benefits. Rob's going to now take a few minutes and go through a review of those 3 R's, and then we'll spend the rest of the time on the presentation talking about the room level and how to optimize the cooling.
Thank you, Lars, and good morning, everybody. So we started this series with a focus on rack level airflow management and highlighted the root causes and negative effects of bypass airflow and mixing of supply and return air. And we described the importance of using blanking panels and other disciplines and other types of barriers to prevent this from occurring. With regard to the floor, and assuming you're in a raised floor environment, it's all about managing the distribution of the cold supply air and giving it a clear path to where it's needed most and preventing it from going to areas where it will be wasted. So using things like floor grommets, fire retardant foam, and other floor specific barriers, those are the best products to use to seal gaps in the floor. And this allows you to focus more on the proper placement and size, percentage of free airflow of perforated tiles used to enable the supply air to reach the IT load. In our last session dealt with airflow management at the row level, and this is where we highlighted and really focused and honed in on the benefits of aisle containment. We discussed the commonly used methodologies for both hot aisle containment and cold aisle containment, and we showed the benefits and differences between modular and mechanically attached containment doors and panels.
All right, thank you very much, Rob. So when any one of those aspects of airflow management has been improved, there's an opportunity to improve the room airflow management. Room airflow management refers to the optimization of the cooling infrastructure. And this is a process that is implemented after all of those airflow management improvements are implemented, that is. So all those airflow management projects are likely an expense. They may improve intake temperature conditions to the IT equipment, but to that point, they are an expense. To realize those benefits, adjustments need to be made at the room level. So cooling optimization is the process of making those adjustments to the controls to realize the improvement in energy efficiency. And those adjustments are typically the changing of fan speeds or the changing of the set points. There's also aspects of relative humidity control. And as we'll get into towards the end of the presentation, there's other benefits to the process. But for the purposes of this webinar, we're going to really focus on what's being done in the computer room. Cooling optimization is an iterative process and one that is made in increments. So adjustments are made to improve conditions, and then you see how those benefits play out. And then further adjustments are made to see how much further the optimization process can go. It's important to recognize that cooling optimization is an ongoing process. It's not just something you do once. The goal of cooling optimization is to provide the appropriate IT equipment intake air conditions and redundant cooling capacity with the lowest possible flow rate of conditioned air at the warmest possible temperature. So that is a long sentence, but that is essentially what this entire presentation is about: taking care of the IT equipment and doing it with the lowest possible flow rate of conditioned air at the warmest possible temperature. And if that is done, the cooling capacity will be maximized, and the efficiency will be maximized, and the operating cost will be reduced as much as possible. So let's get into some more of these details. Cooling optimization is really important because every time there's adjustments in the computer room, and computer rooms are generally pretty dynamic in environments. IT load comes, and sometimes there's decommissioning of equipment and it leaves. And the cooling units don't always make the all the adjustments necessary to realize, to get to the highest levels of efficiency possible once those changes have occurred. The amount of cooling that happens in the room always equals the amount of heat load that is being dissipated in the room. However, it's not always as efficient as it could be. And so that's why it's important to understand this process. I want to reiterate that cooling optimization, without airflow management improvements, without optimization, that is, the airflow management improvements that have been made are an expense. The ROI comes from making these adjustments, and that's the way you get the return on investment. It's been a misconception in the industry that efficiency is something you can buy. It isn't. You can't purchase efficiency. Efficiency has to be managed, and it's through this process that that's done. So let's talk about a very important concept in cooling optimization, which is bypass airflow. Now, bypass airflow has had a lot of misconceptions and mistruths and half-truths. A lot of attention has been paid at, say, the cabinet level, but bypass airflow at the room level is what's really important to understand to get your head around optimization and getting the room as good as it possibly can be. So in these next few graphics, we have a representation of a room, and all the airflow moving through the room is 10 units of air. All air moving through all cooling units of the room is 10 units of air. This could be CFM or cubic meters per hour or liters per second, doesn't matter. We're going to just look at relative volumetric flow rates. And so 10 units of air moves through all the cooling units. So 10 units of air goes under the raised floor. And if you add up all the air that comes out of all the openings in the raised floor, there will be a total of 10 units of air. You see in this example that we have 2 units of bypass airflow leaving unsealed cable openings in each of the rows. And we have 6 units of conditioned air leaving the raised floor through supply tiles into the cold aisle. Then we look at what does the IT equipment require? The IT equipment in each row consumes a total of 2 units of conditioned air. So the 6 units of conditioned air is more than is necessary for the IT equipment, leaving 2 units of conditioned air leaving the cold aisle as bypass airflow. So in this room, we have a total of 6 units of bypass airflow. We have 10 units delivered, and we have 4 units required by the IT equipment. And we have 4 units of bypass airflow out of unsealed cable openings, and 2 units of bypass airflow leaving the cold aisle before passing through IT equipment. And it's important, of course, as Rob mentioned, in managing the raised floor open area to seal those cable openings, and that directs all the conditioned air to the cold aisle. So we now have all 10 units of air flowing into the cold aisle, and the IT equipment, however, still only requires a total of 4 units of conditioned air. And the amount of air moving through the IT equipment is independent of the amount of air moving through the room. So 10 is delivered, only 4 is required. We still have 6 units of bypass airflow in the room. And a lot of people would say, well, all you have to do is put doors and a full roof on this aisle to block that bypass airflow. However, that doesn't block the bypass airflow. You will still have 10 units of air delivered to that aisle. It's true that that 6 units of bypass airflow will not leave the top of the aisle because there's a roof. Where will it go? That 6 units will get pushed through the IT equipment that doesn't need it. So you actually can have bypass airflow flowing through IT equipment. Essentially just more air flowing through the IT equipment than is needed. This doesn't create any particular problems, but it is still wasting fan energy, moving extra air around that isn't needed. It's also reducing the return air temperatures to the cooling units, compromising the efficiency, and we'll talk more about that process in a moment. So sealing the raised floor was a very good thing. It created the opportunity now to reduce the amount of air flowing through the room and balance the ratio of conditioned air to IT demand air. The IT equipment needs a total of 4 units of air. We can now turn off half the cooling units or reduce the fan speeds of the cooling units by half so that we're only delivering 5 units of conditioned air for IT equipment that requires 4. We have 1 extra unit of conditioned air in that cold aisle. That's there to provide a little positive pressure and to have additional capacity for variations in the IT equipment demand. So that's bypass airflow, and it's really important to understand at the room level. It's very just simple to calculate. It's the total flow rate moving through all the IT equipment minus the flow rate moving through, the total flow rate moving through all the cooling units minus the flow rate moving through the IT equipment. What's left over is bypass airflow. Let's move on to another really important topic in optimization, and that is the 4 delta T's. When you ask somebody, what are the delta T's in a computer room, you'll quite often get one of 2 answers. You will either hear people say that the delta T in the computer room is the change in temperature through the IT equipment, or you'll hear people talk about the change in temperature through the cooling units. So both of these, of course, are delta T's, and they are the most common, but there's 2 others that are very important to understanding the process of cooling cycle in a computer room. And it's what is labeled as 2 and 4 on this image. So in this image, we have kind of the ideal situations. You see that the temperature from the time it leaves the IT equipment on its way back to the cooling units is essentially the same temperature. And that's the way it should be. The temperature from the time it leaves the cooling unit and flows towards the inlets of the IT equipment is essentially the same temperature. It hasn't warmed up. And if you look at the legend there, green is somewhere around 75 to 80 degrees. We have warm supply air because the IT equipment can accommodate intake temperatures. ASHRAE's recommended maximum is 80.6 degrees Fahrenheit or 27 degrees Celsius. So that's the maximum recommended, not just allowable, but recommended. And so if the recommended maximum is 80 degrees, then why not supply air that is close to that? But this is not what happens in most computer rooms. We see here on this next image that what is actually occurring is that there are very large changes, very large delta T's in these other 2 locations, that when the air comes out of the IT equipment, it comes out at a very high temperature, usually well over 100 degrees Fahrenheit, 35, 40 degrees Celsius. And yet, by the time that air gets back to the cooling unit, it is much cooler. And when the air leaves a cooling unit, it comes out quite cool. Quite often, that air is only 60, 65 degrees Fahrenheit. And yet, by the time it gets to the inlets of IT equipment, that air has warmed up quite often to somewhere around 75, 80 degrees Fahrenheit. So why are these 2 locations having delta T's, having significant temperature changes when there's no heat source or nothing to cool the air? Well, the obvious answer is that when exhaust air leaves the IT equipment on its way back to the cooling units, extra cold air has mixed in and reduced that air temperature. That extra cold air can come out of unsealed cable openings or misplaced supply tiles, or extra air coming out of the supply tiles in a cold aisle. There's more air flowing through the room, more air flowing through the cooling units than flowing through the IT equipment. and that excess air has to go somewhere, and eventually it mixes before returning to the cooling units, reducing that return air temperature. And on the supply side, why does the air warm up so much from the time it leaves a cooling unit to the time it gets to the warmest inlet of IT equipment? Well, obviously, warm air has mixed in from somewhere. There is exhaust air recirculation occurring, and that exhaust air, whether it went over the tops of the cabinets or through the cabinets or under the cabinets, it has mixed in and warmed up that supply air. So how do we manage this? What's the goal of this? What do we do with this information? The goal is to have these other two delta T's as low as possible. Ideal world, they would be 0. There would be no change in air temperature from the time it left the IT equipment before it returned to a cooling unit, and there would be no increase in air temperature from the cooling unit supply to the IT intake. However, there's a point of diminishing return, and in well-managed data centers, these delta T's can be down to approximately 5 degrees Celsius or 3 degrees Fahrenheit. That's the goal. And they're relatively easy to measure, and I encourage you to do that. And they are a very clear indication of the opportunity for improving the cooling optimization in the room. So let's move on and look at some of the best practices. Room airflow management best practices are as follows. Reduce the fan speeds for units with variable frequency drives, raise cooling unit temperature set points, manage the humidification requirements in the room, and turn off excess cooling units that do not have VFDs. And now we'll go through each of these in more detail. So when we look at fan speeds, it's possible to retrofit cooling units with VFDs or VSDs. They take various different names. The devices, the images on the right are devices that are used to do that. And adjusting fan speeds to meet the actual airflow demand of the IT equipment in the room is the easiest way to manage operating cost. It is the lowest hanging fruit. And whenever consultants come in to help try and save money on cooling, that's what they're looking for first. They're looking for the opportunity to reduce fan speeds because of the fan affinity laws. A 20% reduction in fan speed results in a 20% reduction in airflow, but almost a 50% reduction in the fan energy, the energy consumed by those fan motors. So you see here on this, these images of the fan affinity laws that airflow rate, the volumetric flow rate of conditioned air through a fan, is proportional to the fan speed. If there's a 10% reduction in the RPM, the fan speed, there's a 10% reduction in the flow rate of conditioned air. Pressure is proportional to the fan speed squared. So if there's a 10% reduction in fan speed, there's a 19% reduction in the static pressure. And power consumption, here's the real benefit here. Power consumption is proportional to the fan speed cubed. So if you reduce the fan speed by 10%, there's a 27% reduction in energy consumption. Or as I just mentioned before, a 20% reduction in fan speed gets you nearly a 50% reduction in energy consumption. And you take that even further, a 50% reduction in fan speed gets you over an 80% reduction in fan energy. We're not talking single-digit improvements. This is 80% reduction in fan energy. So it's really important to look at bypass airflow and understand how much lower those fan speeds could be if the airflow management in the room is improved. Let's look at the next topic of improving efficiency, which is raising set points. By implementing these airflow management best practices at the raised floor, the rack, the row, and the row, IT intake temperatures become lower and they become more even. And that enables the adjustment of the supply temperature. And this is true of whether it's a return air temperature controlled system or a supply controlled system. Adjustments can be made to increase that supply temperature, and therefore the return air temperature increases as well. And the higher the return air temperature to a cooling unit, the more efficient it is, and the higher the capacity that it has. Here's an example of a Liebert chilled water unit. And this is a cherry-picked example to just really point out the dramatic benefits that can be achieved by small changes. So you can see here that a return air temperature of 70 degrees Fahrenheit on that second row results in a 48% relative humidity. And at those conditions, this cooling unit has a total capacity of 64.5 kilowatts. It has 4.8 kilowatts of latent capacity at those conditions. What that means is that 4.8 kilowatts of that cooling unit's capacity are taken up by removing the heat given off by moisture condensing on the coils. Latent heat or latent cooling, as it's sometimes referred to. So we want to remove the latent cooling. We want to remove the condensation on the coils. And when we do that, by just raising the supply temperature, in this case 2 degrees, the relative humidity drops to 45%. The total capacity of the cooling unit goes up to 67%. And since there's no more condensation occurring on the coils, there's no cooling capacity consumed by that latent heat. And all of the capacity is sensible at 67 kilowatts. So that's an 11% increase in the sensible cooling capacity of that cooling unit with just a 2-degree change in return air temperature. Now, as I mentioned, this is a cherry-picked example. Obviously, if you go from 72 degrees Fahrenheit to 74 degrees Fahrenheit return air temperature, it won't be as dramatic because we've already gotten rid of the condensation on the coils. However, there are a lot of facilities that are operating with a small portion or a substantial portion of condensation occurring on their coils. And that's consuming a lot of energy and has the adverse effect of also removing the moisture, often requiring humidification to get that moisture back into the air. So let's talk about that a moment. Humidification control in the computer room is another very important aspect of saving money. Humidity control is most effective when it's applied as part of an overall strategy. It's most effective when humidification and dehumidification control, and that process is done from a centralized location. And all the humidification and dehumidification functionality in the individual cooling units is turned off. Either that way or with cooling units that are talking to each other and they know what each other are doing. Because as many of you have probably heard, cooling units can fight each other. One cooling unit can be trying to provide humidification, and right next to it is a cooling unit that is attempting to dehumidify the air. And this consumes a great deal of energy. So let's look at when you do not have the ability to reduce fan speeds, just turning off a cooling unit. How much energy is there consumed by these fan motors? So a typical large cooling unit that might have 2 10 horsepower or 7.5 kilowatt fan motors consumes 15 kilowatts of electricity 24 hours a day, 365 days a year, of course. And at an average cost of 10 cents a kilowatt hour, that results in over $13,000 of electric bill for that one cooling unit. So if you can turn off a cooling unit, you can save $13,000 a year. That adds up a lot, and that number is even greater if there are variable speed drives on the variable frequency drives on the cooling units. you have greater energy savings if you reduce the fan speeds of all the cooling units in the room compared to turning off several of the cooling units in the room. It's necessary to implement airflow management best practices to the full extent possible to maximize the number of cooling units that can be turned off, or to maximize the fan speed reductions that are possible. So with that, I'll turn it back over to Rob, and he can share some other solutions that are available to help manage this process.
Thank you, Lars. That was some great information. We've talked about the importance of matching cooling capacity to IT loads, and now we're going to take a closer look at ways this can be accomplished and some of the tools that can be used to help. We recently published an article in Mission Critical where we quoted Ken Brill, one of the founders of the Uptime Institute, who said, when it comes to data center cooling, it's as simple as power in, heat out, always. So in other words, every kilowatt of power consumed in a computer room becomes a kilowatt of heat that needs to be removed from the computer room and ultimately the building. This includes all the power conversion and distribution losses, as well as every kilowatt of electricity consumed by the IT equipment. So how do you know how much power is being consumed by your IT load? And how do you know how much cooling is required to properly cool that load? Monitoring tools help provide the answer. So let's talk a little bit about that. There are many different ways of monitoring data center power and cooling. There are visual, call it at-the-rack meters on many of the different power strips that can be added and aggregated. And a best practice would be to have those metered power strips be network attached so that some more sophisticated software can manage those strips and look at their deployment as a whole. There are also higher level standalone monitoring software programs available from the PDU manufacturers or even DSIM providers, and there are similar packages available to assist with managing the mechanical or the cooling infrastructure. So use of these types of tools can assist in determining and validating your load and cooling requirements. Here are additional examples of tools that are or can be used to monitor and capture power, cooling, and some of the environmentals like temperature and humidification. So you've got technology, communications technology that can network your air conditioning unit infrastructure. So they're not operating as individual standalone units. And I think Lars and I can tell you that we've been in so many data centers where you have a lot of perimeter AC units and you're looking at two next to one another, and one's heating, one's cooling, one's humidifying, one's dehumidifying. They're fighting one another, consuming lots of unnecessary energy, and it's not very efficient at all. So there's communications capabilities and from some manufacturers that allow you to network your AC units and manage them as kind of a team. Next, you've got kind of like your basic flow hood or bolometer that are commonly used to measure flow and capture other airflow metrics kind of at the floor tile or at the ceiling register. So those are used throughout the data centers on kind of a one-by-one basis or in contained aisles. You've got mass airflow sensors that are placed in the return air stream of AC units to help measure enthalpy. You've got a variety of different temperature and humidification measuring capabilities, from tethered sensors that report back to a system you're looking at on a screen. You've got handheld infrared temperature measuring that have temperature gradients as well, like a FLIR gun. And you've got some temperature and humidity that actually have local digital readouts in addition to what they can communicate back. And then in the bottom right-hand corner, these are CTs, or current transducers, and you can either have a closed or an open CT, and these are clamped onto the electrical inputs to fan motors and compressors and things of that nature to help measure energy consumption real time by that unit. Next slide. So if you don't have metered power strips or any higher end monitoring software or fancy tools, let's start with some basics. And we talked about this in one of the previous webinars, but here's some simple math. Let's start by converting tons of cooling to kilowatts, right? So count them up. How many units do you have? What's the total tonnage across all of those AC units? And then multiply that number by 3.52 to obtain the total cooling capacity in kilowatts. And remember, watts is the common metric we're going to use. So it's real easy. Once we get everything converted, now you can compare a watt of cooling to a watt of IT load. So your IT load can be, simply gathered by reading the UPS display or an output load from some monitoring software, but you can grab the IT load off the UPS, and that's usually already in kilowatts. So now that we have both of those metrics, the cooling capacity and the IT load, we want to try to do a comparison, right? So those last two bullet points are important here. When you're matching the IT load with cooling capacity, you want to see some kind of ratio, ideally in the 1.2 range, which is a little bit more headroom, a little bit more cooling capacity than you have IT load. That gives you some redundancy and keeps things like aisle pressures a little bit positive and contained aisles. But in most cases, and what we found over the years, this is not a new phenomenon, but ratios are a lot higher, right? You have a lot more cooling capacity than you require to cool the IT load that you have. And this is where the inefficiency lies. This is because of all the mixing and all the science that Lars just went through. So once you see that you've got some kind of ratio that's like 2 or above even, and we've seen some way high, this is, I look at it, not as a problem and an oh my, this is an opportunity for cooling optimization and to pick up some efficiency. So as far as the higher end software tools are concerned, there's a lot out there, and a lot of it's being used today, and some of it's probably being used by a bunch of you that are on this presentation. But just to kind of go through what some of the tools people are using, and again, our industry loves the acronyms, right? So the BMS, the building management software, that stuff's used to control and monitor the building's mechanical and electrical equipment like ventilation, lighting, power systems, fire, security. Lesser used kind of electromechanical software, which is more focused specifically on the mechanical systems in the facility. Then you've got the all-encompassing kind of DSIM tools, and that started out as a heavy buzzword, and then it became like the D word that you don't want to use, right? So it's a all-encompassing tool set used to monitor, measure, manage, and sometimes control data center utilization, maybe manage energy consumption. It touches both IT and facilities. So it's very powerful and, again, all-encompassing. But that all-encompassing nature makes it very complex to sell, very complex to install, use, the commitment from the stakeholders in the organization, and because it crosses a lot of functional areas of a business. Computer or computational fluid dynamics, or CFD, is probably no better tool out there to do simulations for airflow and to do digital twinning. It's not necessarily a monitoring tool. There may be things evolving with regard to that, but now this is a perfect simulation tool, but not a good monitoring tool. And lastly, you've got some real-time use through machine learning and artificial intelligence. And this is some of the newer technology that we're going to talk a little bit more about. So on that note, as our industry and world seem to technically evolve at a rapid pace, we hear more and more about the use of artificial intelligence and machine learning. And I think we all have some level of fascination or maybe even a fear with some of the things we've heard and its potential uses and capabilities, whether they be good or bad. Next slide. But, as we mentioned in the article we recently published in Mission Critical, those two bullets are important, right? AI and machine learning have been buzzwords that have been used in our industry. Our industry is great for latching on to buzzwords and just kind of running with them, right? And there's been a lot of promises, you know, this might be the holy grail. Talked to someone the other day about this may be like the Alexa for data centers. So there's been some promises, both perceived and marketed, that have come up short in the past. But, you know, now with where technology is headed and the dedication to some of this as it relates to airflow management and cooling, this is really where this technology is going to have a chance to deliver and shine. So now imagine, if you will, the ability to have a sensor. Sensors are key in all of these solutions, right? So that you have your sensor network all throughout your data center. So now imagine the ability to use real-time sensor data, create a digital twin of your data center layout, and then visually represent your current and thermal conditions, and then provide recommendations for optimization, and have the system know when those changes were made, and have the system update that digital twin to reflect the changes. You know, this is the direction where airflow management's headed with regard to AI and machine learning. So I'm going to deviate on a little bit of a tangent here, but on a side note, I don't know if how many of you may have caught that Q2 critical update presentation from the Uptime Institute a week ago on May 20th. But it was their quarterly update. It was presented by their director of research, their VP of research, and their CTO. So high-level people within the organization. And it dealt with a variety of different data center operations issues, mostly all around this new normal of working through the pandemic. They talked about how to deal with resiliency, maintain uptime, dealing with equipment maintenance, site access. All these things were discussed in addition to a theme called the role of automation in the years ahead. And they did a global survey of end user customers. And the results that came back with regard to an increased interest in pursuing automation in the data center were very interesting. And kind of here's a quick overview of some of those comments, and then we'll tie this all back together, right? There going to be a increased focus on the return to automation in the data center, including remote call and management. And you know, we've seen automation kind of drop off a little bit as other systems became more robust in, you know, managing discrete aspects of a data center. But remote management is now even more important with thousands of people now working out of their homes. That equals the increase in need for remote managing and monitoring. And that also reduces human intervention, which, as we all know, is pretty much one of the leading causes of downtime. And in fact, with regard to downtime, they talked about 10% of those respondents in their survey had a severe outage in the last 12 months, 21% had serious outages, and 47% had what they called notable outages. And most of those had to do with bandwidth and IoT issues, believe it or not. And this one got me. So more end users have contacted the Uptime Institute about reconsidering a DSIM implementation in the last month than they had in the previous 12 months combined, right? So more people contacted them in the last month than in 12 months combined about considering going towards a DSIM solution. You know, but they caution, right? They say due to the generally heavy resource requirements for both the vendor and the client, and then coupled from today's work from home environment, they said now is a great time to take on budgeting and implementation planning, but not a good time to actually do the implementation of a DSIM tool. And lastly, at least for now, an increased interest in the cloud. So companies that may have been on the fence in the past about pushing some applications to the cloud may be reconsidering it and moving in that direction. That said, their survey did show that 52% of mission critical workloads are not going to be going to the cloud, and customers don't plan on sending them to the cloud. But the big cloud providers continue to invest in real estate and facilities to support their expected growth. So let's go back now to considering the use of AI and machine learning for airflow management and cooling optimization, kind of as that third bullet shows, right? So you've got the ability to help visualize airflow management and analyze the data being collected from the sensors and provide advisement. So that's really important. So let's see what some of this might look like, right? So you've got the ability, let's just say, to see a digital twin of your data center broken down into different color-coded zones of influence for the air conditioning units and the racks and loads they support. Real easy. You've got like kind of 8 or 9 cooling units here. Every one of them is represented by a different color. And then the rows of racks that are closely aligned with the cooling production of that AC unit are similarly color-coded. Real easy to look at, right? Then you kind of move on and you can do the same thing with temperature. Next slide, please. You can do the same thing with temperature. You can have your gradients, you can have your different color coding and your different representations of the ranges of the temperatures, and then see a nice, that same digital twin represented with the different color gradients of the racks. And then this is where the kind of the really cool stuff starts to happen, right? You've got, the next slide, please. You've got built-in really high-end complex algorithms around the science of airflow management and cooling that are now going to look at what's going on, decide on where maybe some inefficiencies are, and make a recommendation to you on how to optimize your environment. This doesn't happen with software. You get a ton of data. The tools from the vendors today provide tons of data, all the data you'd probably need, but you got to manage it. You've got to make it actionable. You've got to put it into represent it internally in a way that you can actually make good decisions on what to do with it. Here you've got, something that's telling you what to do. In this case, it's telling you to place AC handler into a standby mode. And then finally, the kind of the resulting thing, you can look at befores and afters, right? So that once you're done, you can visually see the before and after effects of your changes. And in this case, we're taking a data center that had a lot of overcooled areas in the left and blue, and one overly hot area there in that kind of the top right corner. And then after implementing recommended optimization steps, resulted in a more uniform temperature profile across the entire space. So these are some things to be on the lookout for or consider, as we migrate through this new normal, work from home, maybe not have resources on site, but you've got artificial intelligence and some machine learning that could be doing that on-site work and making those remediation recommendations for you. All right, so we've pretty much come up on the end of the presentation. I wanted to thank all of you who attended and stuck it out through now. We know today was a busy day as far as web presentations go. There was a lot going on. We really appreciate you attending ours. So I'm gonna go through some of the key takeaways, and I think Isaac this will be made available after the presentation's over. But, we talk the top 3 of not necessarily airflow management, but cooling optimization, especially when we get to the room level. And like Lars said over and over again, right, it's the only way to realize energy savings. All that stuff you've done, all those blanking panels, those floor grommets, those barrier panels, those aisle end doors, all of that stuff up until now has been an expense. But it's your ticket to the dance, and now it's your turn to help realize it. So it's an iterative process and ongoing. You can take it in small, little incremental improvement chunks, but at the end of the day, when you need to realize the savings, it's up to you to kind of make these improvements that we've learned about today. The use of monitoring solutions is important. It's your level of kind of sophistication in the data center and kind of what you can afford from a budget standpoint, but really gone are the days where you've got the know-it-all guy that walks through with the Excel spreadsheet and kind of takes readings and manually records things. You've got some sophisticated tools that can do this work for you and make the proper recommendations for you. And lastly, the optimization obviously improves efficiency, reduced operating costs, and can actually give you the ability, some headroom to increase capacity in that same space. And with that, I'm going to turn this back to Lars because he's got some bonus insight on some additional benefits of cooling optimization. Lars?
Yeah, thank you very much, Rob. Yeah, so much here. And as I said in the beginning, we were going to focus on the computer room envelope, but there's some other very substantial benefits that should be considered when putting together a business case for any of these improvements. This is that list. There's going to be a reduced infrastructure maintenance cost. By putting cooling units in standby, they can be taken off of the maintenance schedule and just placed in inactive standby. There's an increased availability of free cooling hours. This can be massive. So by increasing the supply air temperature, the number of hours where the outside air temperature is that much warmer can be dramatically increased, and so free cooling can have a much greater return. There's the ability to increase chilled water temperatures for chilled water plants, and that can also be quite substantial in improving the chiller efficiency, as chillers consume a great deal of energy. And then more on the business side, for co-location facilities, there's an increase in the number of customers and or the amount of power that can be sold per suite before those ceilings are reached, before those limits are reached on keeping the IT equipment happy and maintaining those SLAs. And then ultimately, this relates to deferring capital expenditure, not just from additional cooling units, but all the way up to the building of a new data center or a addition to a computer room. We know of a couple of different sites, one in particular that they had already begun the planning processes for building a new data center, thinking that they were at the limit of what they could do with where they were. Airflow management, cooling optimization efforts were taken place, and they were able to stay there for an additional 2 years. So 2 years of deferred capital expenditure for building a new facility resulted from just, blanking panels, grommets, and making some adjustments to the infrastructure. So huge benefits from all of this.
All right, great job, Rob and Lars. I think that was a really good presentation. Looks like we got quite a few questions coming in, so I'm just going to jump into them right away. There was a question about if this presentation will be provided after, and the answer is yes. We will provide both a PDF of this presentation as well as the recording to all attendees and registrants within the next couple of days. There's also a question about the mission critical article that was referenced. So William, I did send that to you directly, and I also sent it through the chat if anyone is interested in reading that article. All right, let's jump to the first question. What's the best way to measure delta T's?
I'll go ahead and take that one. So there's a number of different ways to measure delta T's. It can be as simple as with an infrared thermometer or an infrared camera. Taking into account that infrared measurement devices can't actually measure air temperature. They measure the temperature of surfaces. But in the right location, those surfaces are the same temperature as the air flowing over them. So that's the easiest way, the quickest way to get a sense of what's going on. And if you want to go into more accurate measurements, then going into other thermistor type measurement devices are appropriate. And some of the information is available from the displays, from the cooling units themselves are going to tell you potentially what both the return and the supply air temperatures are.
All right, thanks, Lars. Moving on to the next one. Is cooling optimization different for hot aisle or cold aisle containment?
That's a good question. It isn't, and that's why we didn't get into that distinction. And we also, although we talked about raised floor spaces and not particularly slabs, the concepts of bypass airflow and the 4 delta T's apply equally to hot aisle containment, cold aisle containment, and slab environments with hot or cold aisle containment. All those concepts apply. equally and can all be measured and utilized in the process of optimization.
Got it. Thanks, Lars. Now, we got another one here on containment. Looks like a specific use case. My environment is in a cage in a large room at a colo, and I notice it's warmer than usual in our cage. Can containment be installed in my cage, and how is that accomplished when there are other customers in the same room?
I'll take this one. So we see that a lot, especially working in co-locations. So you've got a couple dynamics there, right? You've typically got a large room, like a big data center room that's segmented into smaller pods or cages that could be anywhere from just a couple racks to like 20 racks. But you've got a cage around it, you know, and that's your space. That's your little data center. And right next to you is another guy's who has nothing to do with yours except your being fed, so to speak, from the same kind of cooling infrastructure and maybe some from the kind of same power infrastructure. So your heat related issues or what you're perceiving may not be things that you're actually causing, right? It could be your neighbor, it could be large network switches blowing hot air directly into your, call it, cold aisle. So there are a number of things that can be done to remediate this, but it all has to be done in the context of improving your situation without making someone else's worse, whether it be a client in that room or the actual colo itself. So we try to make sure that there's always a clear path for the return air to get back to the air conditioning units. That's key. We don't want to ever block that from happening. And then we actually get involved with panels that actually are applied on the cage as barriers, perhaps between your neighbor's hot aisle and your cold aisle, where all that's separating that is, you know, a couple tile spaces and the actual vertical cage itself. So we get involved. We do usually on-site kind of assessments and look at what's going on and make sure that what we're going to propose is appropriate not only for you to remediate your issue, but we're not going to make anything worse, both in that room or for your neighbors.
All right, thanks, Rob. Looks like the next one is for Lars. Lars, can you list your formula for the total flow rate rolling through IT equipment minus?
The flow rate through IT equipment is determined by a couple of different factors. The IT load in the equipment, how much power the IT equipment is consuming and dissipating, and what the delta T is through that IT equipment. So that's a little more than I can relay verbally. Typically, the flow rate is approximately 155, 160 CFM per kilowatt. That's for a delta T of around 20 degrees Fahrenheit through the IT equipment. So that's a good starting point, is to take the IT load and multiply the IT load times 156 CFM per kilowatt to get what the total flow rate is through the IT equipment. More specifics require determining what the delta T is through the individual pieces of equipment, and then looking up the flow rate for those different delta T's. And if you would like to have a conversation about that, I have some tables that I can provide offline.
Yeah, and what I would add to that is, I mean, that's another handy kind of metric, right? That, call it 160 to 200 CFM per kilowatt. Because once you get into aisle containment, and now you're only provisioning the air going into that aisle, like your gear's not just pulling it from wherever. Now it's important that you've got to match the flow rate requirement to what that IT load is. So that, you know, that bolometer I showed, that flow hood, that helps measure flow in the individual aisles. But the last thing you want to do is contain an aisle that you're going to starve because you can't deliver enough supply air into that. So it's also an important balance to make sure that when you move towards aisle containment, that your infrastructure has the ability, you've enabled your infrastructure to deliver the amount of flow required for the load in that aisle.
Yeah, certainly.
All right, thank you both. We are at the top of the hour here, but we're going to get through just a couple more questions. If we don't get to yours, we will follow up with you after the presentation. All right, the next question here is, which software is used for AI?
You want to take that, Lars?
Sure. So the examples that Rob showed of the AI solutions and the machine learning available is a package called EchoSense. And it's a combination of sensors, the thermal, temperature and relative humidity sensors that are placed on the cabinets, as well as a cloud-based software solution with some pretty sophisticated algorithms written into it to provide those recommendations and all those graphics.
All right, thanks, Lars. Another one here, let's see. How can we measure the CFMs delivered by a CRA unit if equipment doesn't show it?
So let me follow up on that last question real quickly. So EchoSense is something that you can contact Rob about. That's something that he has information about that solution. And the CFM through cooling units can be a little tricky to measure, but there's a number of devices available. Rob showed a couple of airflow meters that are used. Some of those can be put in permanently, and others are used just as handheld devices to measure the airflow. It's essentially measuring the velocity of the air over the area that it's returning to the cooling unit and multiplying that velocity, that average velocity times the area to get the flow rate. Well, and once that's done, then and calibrated, the cooling units or modern cooling units provide that information.
Got it. Thank you, Lars. Well, we are about 2.5 minutes over the hour here. For those of you, if we did not get your questions, we will follow up with you after the presentation, or please feel free to email Rob or Lars at the emails provided on this last slide, and they can follow up with you directly. Thank you again for everyone who attended this webinar. Rob and Lars, thank you both for presenting. Please feel free to add any closing comments before we end this.
I just want to say thank you to everyone for your time, and look forward to following up with any detailed questions you have.
Yeah, likewise. It's been my pleasure to be on this series with our friends at Upsite, and look forward to answering the rest of the questions, and I hope everyone still remains safe and healthy as we navigate through this new normal. Have a great day, everybody.